So a function f has derivatives of all orders at x equals 0. Let Pn of x denote the nth degree Taylor polynomial of f about x equals 0. It's known that f of 0 equals -4 and that P1 of 1/2 equals -1. Show the first derivative at 0 equals 2. So they gave me a Taylor polynomial of degree 1. So I'm going to go ahead and write out the terms for a Taylor polynomial of degree 1. So a P1 of x for a Maclaurin is equal to f of 0 over 0 factorial x minus 0 to the 0 plus the first derivative at 0 over 1 factorial x to the first. So a P1 of x is equal to f of 0 is -4 over 0 factorial is over 1 times 1 plus f prime of 0 x to the first over 1 factorial is over 1. Now I'm trying to show that the first derivative is equal to 2, so what I'm going to do is plug in everything they gave me. So that they told me a P1 of 1/2 is -3, so -3 equals -4 plus f prime of 0, and x in this problem is 1/2. So when I add 4 here, I get 1 equals f prime of 0 times 1/2. And when I multiply both sides by 2, that gives me that the first derivative is equal to 2. So I showed that the first derivative was 2. Now they are telling me the second derivative and the third derivative and asking me for a P3. So 3 means it's going to the third degree. So Pn of x equals, now if I'm going to a third degree, that n is 3. So it's going to be f of 0, x to the 0 over 0 factorial, plus the first derivative at 0, x to the first over 1 factorial, plus the second derivative at 0 over 2 factorial, x to the second, plus the third derivative at 0 over 3 factorial, x to the third. So in part A, I just needed this much and I plugged in everything I knew. In part B, it's just asking me to find this Taylor polynomial. So from part A, I already know that my first two terms. So this is -4 over 1 times 1 is -4. Plus this was 2 over 1 times x to the first is just 2x. So that I got from the top. And now plus the second derivative is -2/3 times 2 factorial is times 2 times x to the second, plus the third derivative is 1/3, and then over 3 factorial. 3 factorial is 1 times 2 times 3 is times 6, x to the third. So my P3 of x equals -4 plus 2x minus 1/3 x squared plus 1 over 18 x to the third. So that's a P3. And if I wanted to plug in 1/2, I could have found a better approximation than -3. Remember, the more terms you have, the more accurate your approximation is. Now, let the function h, the function h has first derivative given by h prime of x equals f of 2x, and it is known that h of 0 equals 7. Find the third degree Taylor polynomial for h about x equals 0. So h prime of x is equal to f of 2x. So everywhere up here I have an x, I'm plugging in a 2x because this is the same as f of x. So this is going to be negative 4 plus 2 times 2x minus 1/3 times 2x squared plus 1 over 18 times 2x to the third. So h prime of x is equal to negative 4 plus 4x minus 2 times 2 is 4, so negative 4/3 x squared plus, that's 8 over 18, x to the third, so 4/9, x to the third. So this is h prime of x. It is known that h of 0 equals 7. This is an initial condition. Find the third degree Taylor polynomial of h. So it wants me to integrate this thing. Now, here's the thing. When I integrate, I'm going to go up by 1 degree. So do I have to integrate this piece? Nope. This piece is going to go away because when I integrate this piece, it's going to be a third degree Taylor polynomial. So h of x equals negative 4x plus 4x squared over 2 minus 4/3 x to the third over 3 plus c. I now have a third degree Taylor polynomial. I didn't need that last term. So h of x equals negative 4x plus 2x squared minus 4/9 x cubed plus c. And the reason they gave me an initial condition is so that I could plug in the initial condition and solve for c. So h of 0 is 7, so this is going to be 7 equals negative 4 times 0 plus 2 times 0 squared minus 4/9 times 0 cubed plus c. So c is just equal to 7. So my h of x equation is negative 4x plus 2x squared minus 4/9 x cubed plus 7. Box it up, you're done. Thank you.